Hello and welcome. You know, if you've ever watched a baseball soar through the air or seen a firework burst in the sky and thought, how does it do that? Well, you're in exactly the right place. Today, we're going to pull back the curtain on projectile motion. And I promise, by the end of this, you won't just get it, you'll know exactly how to solve for it. All right, let's just jump right in. When you throw something, anything, it makes that classic curved path, right? And it seems like one single, pretty complicated motion. So how in the world are we supposed to predict where it's going to be at any given moment? This, right here, is the big problem we're going to solve today. First things first, let's make sure we're all on the same page. The thing we're talking about is called projectile motion. It's really just the path of any object, we call it a projectile, that's moving through the air with only one thing bossing it around, gravity. Now, to make things simpler, we're going to ignore air resistance for now. So here's our game plan. We'll start with the problem itself, then I'm going to let you in on the big secret that makes this whole thing way easier. We'll break the motion down into its horizontal and vertical parts, put it all back together to solve a real example, and then we'll see how this one little idea scales all the way up from a simple throw to, planetary orbits. Okay, so let's go back to that curve for a second. It doesn't matter if it's a football, a firework, or even a stream of water from a fountain. That arc, that parabola, it just looks like one single tricky thing to figure out all at once. But here comes the breakthrough. This is the single most important idea for understanding any of this. It's called the independence principle, and trust me, it's the secret key that turns complicated projectile motion into something really, really simple. And here it is. This is the big aha moment. You don't look at it as one complex motion. Nope. You break it down into two totally separate and much, much simpler motions that just happen to be going on at the same time. You've got the sideways motion and you've got the up and down motion. That's it. And this isn't just a neat trick, it's fundamental physics. This quote from our source material says it all. Motions along perpendicular axes are independent and can be analyzed separately. Seriously, this is the key. If you walk away with just one thing today, make it this. All right, so let's actually put this principle to work. We're going to start by looking at the first of our two separate little worlds, the horizontal motion. I like to call this one the constant world. See, in the horizontal direction, along the x-axis, gravity isn't pulling it left or right. So that means the horizontal acceleration is just zero. And what happens when there's no acceleration? Well, the object's forward speed never changes. It just keeps on cruising at the exact same speed it started with. Simple as that. Now let's look at the second, totally independent world, the vertical motion. This is where gravity gets to be the star of the show. So here, on the y-axis, the object is constantly being tugged downward by gravity. And this gives it a constant downward acceleration of negative 9.8 meters per second squared. Because of that constant pull, its vertical speed is always changing. It slows down on the way up, stops for just an instant at the very top, and then speeds up all the way back down. And this lays it all out perfectly, doesn't it? On one hand, you've got this simple, unchanging horizontal motion. And on the other, you've got this constantly changing vertical motion. By looking at them separately, we've turned one hard problem into two pretty easy ones. Okay, so we've got the theory down pat, but how do we actually use this to solve a problem? Let's walk through the exact steps. So the process is always going to be the same, and it's just these 4 steps. 1, you break up that initial launch speed into its horizontal, or x, part, and its vertical, y, part. 2, you treat them like they're two completely separate one-dimensional problems. 3, you solve for what you need in one dimension to find the time it's in the air. Time, you see, is the crucial link. The object can't be in the air vertically for a different amount of time than it's in the air horizontally, so time connects the two worlds. And 4, you just use that time value in the other set of equations to find your final answer. Let's make this real with a great example from the OpenStax text. Let's say we're launching a fireworks shell, and what we want to know is, how high is it going to go? Okay, here's what we know. The shell shoots out with a speed of 70 meters per second at a pretty steep 75-degree angle. We've got everything we need to use our 4-step method. So remember, this is the most critical piece of the puzzle. As that firework is moving sideways and moving up and down, the one thing, the only thing that ties those two separate journeys together is the clock. The amount of time it spends moving forward has to be the exact same amount of time it spends going up and down. Okay, so let's look at the vertical motion first. From step 1, we know its initial upward speed. And we know that at the very, very top of its path, its vertical speed will be 0 for just a split second. Using one of our standard kinematic equations for the vertical part, we can solve for time. And that calculation tells us it takes exactly 6.90 seconds for it to reach the peak. And now we have our link. We can take that time, that 6.90 seconds, and plug it right back into another vertical motion equation to solve for the height. And when we run the numbers, boom, there's our answer. The shell gets up to a maximum height of 233 meters right before it explodes. See? We kept the two worlds separate, used time to connect them, and it worked perfectly.
But look, this whole independence principle isn't just for homework problems. It explains the motion of everything from a casually thrown baseball all the way up to an orbiting satellite.
You know, one of the most common things people want to figure out is the range. And that's just a fancy word for the total horizontal distance the projectile travels. Back in the day, this was, as you can imagine, super important for things like aiming cannons. So what determines the range? Well, it mostly comes down to two things: how fast you launch it and the angle you launch it at. And here's a neat little fact for you. If we ignore air resistance, you will always get the farthest possible distance by launching something at a perfect 45-degree angle. Now let's take this whole idea and push it to the absolute limit. What would happen if you launched a projectile with just a ridiculous amount of speed, so its range is massive? Well, as it flies forward, something really amazing starts to happen. The Earth, because it's a sphere, actually starts to curve away from underneath it. And that brings us to this final, just mind-bending thought. If you throw something fast enough horizontally, it will fall towards the Earth, but the Earth will curve away from it at the very same rate. It is constantly falling, but it never ever gets any closer to the ground. So what is an orbit really, if not just a projectile that's forever falling but always missing its target?